about recent applications of the pure Spinor formalism.
Okay, so I'd like to start by thanking the organizers. So I will talk about some recent applications of supersymmetric formalism, which can be thought of as an alternative to the Green-Schwarz, which is easier to quantize. So it's been called the pure Spinor formalism. So just to give some motivation about why one is interested in supersymmetric, space-time supersymmetric formalism, let me just remind you that if you're discussing open superstring theory, then we have four different sectors. We have Navier-Schwarz GSO plus, Navier-Schwarz GSO minus, Ramon GSO plus, and Ramon GSO minus. Now, if you want to discuss the Navier-Schwarz either in GSO plus or GSO minus, it's more convenient to use the RNS formalism because there we have worldsheet supersymmetry, which in some sense relates these two different sectors. But if, on the other hand, you want to describe the GSO plus sector, so the vertical line either in Navier-Schwarz or Ramon, it's more convenient to use a formalism which has manifest space-time supersymmetry, in which the Navier-Schwarz GSO plus and Ramon GSO plus sector are described in a simple way. So it depends what you want to do, but if you want to describe space-time supersymmetric processes, for example, multi-loop scattering amplitude, it's much easier to use the pure Spinor formalism than RNS just because you don't have to sum over spin structures, which is essentially the way the RNS formalism compensates for not describing the GSO plus sectors in a simple way. Similarly, if you want to describe backgrounds which have Ramon-Ramon fields, then of course it's much easier to use this formalism just because the RNS formalism is not convenient for describing Ramon backgrounds. Okay, of course one also has the Green-Schwarz formalism, which has essentially the same features as the pure Spinor formalism, but it's difficult to quantize. So as we will see in the pure Spinor formalism, quantization is straightforward. So there are some things that are not natural to describe in the pure Spinor formalism. So for example, if you want to discuss tachyon condensation, it's much more natural to use the RNS formalism just because you're describing these two sectors. Okay, so let me just give a brief outline of what I will talk about. So I will start by just reviewing the pure Spinor formalism. So there were some early papers where some features of the pure Spinor formalism were already present, and essentially it started in 2000, and since then there have been various people working on it, and I apologize if I've forgotten some of the names. So the second thing I will talk about is one application which was recently found, which is to discuss higher G-Levar to the fourth theorems. So these were actually motivated by some work of Green, Russo, and Van Hove, and also, of course, Byrne et al. And the idea is to explicitly compute superstring multi-loop amplitudes, at least the low energy contribution, and see at what Jordan derivative they start at. So at one loop it's known that it starts at r to the fourth, but in fact if you go to two loop it starts at d to the fourth r to the fourth, and the question is how that extends to higher loop amplitudes. As we will see using this formalism, it's very convenient for computing at least the low energy contribution, and what we'll find that this type of behavior works up to genus 6. But at genus 6, essentially this behavior stops, but beyond genus G, at least there's no evidence that d to the 12r to the 4th does not appear, and this suggests, using the arguments of Green, Russo, and Van Hove, that n equals 8 equals 4 supergravity is finite up to 8 loops, but not beyond. Okay, so the last subject I will talk about is some new work that's looking for a topological A model description of the string on ADS 5 times S5. And what I will discuss today is, at least for the superparticle on ADS 5 times S5, it seems that it can be described as some limit of a topological A model, so I will describe how that works. So this is crucial here that you have to use the pure Spinor formalism and not the Green-Schwarz formalism. And this might be useful, so the motivation for looking for this topological A model is to try to generalize the proof of counterfold duality, which was shown by Gopakumar and Vafa and Oguri and Vafa, to Maldacena conjecture. Okay, so let me start by just talking about the basics of the pure Spinor formalism. So it has worldsheet variables, which are these XMs and these fermionic matter variables and bosonic ghost variables. So, of course, in Green-Schwarz, one has these XM and theta alpha variables, but in the pure Spinor formalism, one also has conjugate momentums to theta and these bosonic ghosts, which can some sense be thought of as gauge-fixing kappa symmetry. That's why they're bosonic but have space-time Spinor indices. The worldsheet action is very simple. This is just for the left movers. But lambda alpha is not an ordinary bosonic spinor. It satisfies this pure Spinor constraint, which is called a pure Spinor because Cartan discussed these spinors, and in 10 dimensions it turns out that it has 11 independent components which parameterize this space, so after doing Wick rotation to SO10. Now you might be worried that it's difficult to compute correlation functions, or OPEs, with these constrained variables, but it's not so difficult, and in fact, it can be described using what's called curved beta gamma system, which is shown by Nekrasov to be able to describe these W lambda fields. Okay, just to show that the theory is consistent, at least for the usual conformal anomalies, it's easy to count the conformal anomaly. What gets plus 10 from the x's, minus 32 from the thetas and p's, and the bosonic ghosts give 22. Now this is in conformal gauge, so there's no extra BC ghosts, and that's a slightly confusing feature, but we'll see this is already gauge fixed, in a sense, it's already in conformal gauge. Now, of course, you could do that with 22 scalars, but it turns out that if one looks at the Lorentz current, one can see that the level of the Lorentz current matches the desired level of the RNS Lorentz current exactly if these lambdas are SO10 representations which are pure spinors. Okay, so in addition to these simple worldsheet variables, one also needs some kind of BRST operator. There's no BC ghost, but there is this lambda pure spinor ghost, and it's natural to couple it in a BRST operator to these Dirac constraints, which of course are well known in the Green-Schwarz formalism. So in Green-Schwarz formalism, these are weakly zero, but in pure spinor formalism, they're actually independent variables which are constructed from the p's, the conjugates to thetas, and the other variables. Now, of course, these have first-class and second-class pieces, which would normally mean that the BRST operator is not nilpotent. But in fact, the pure spinor constraint exactly compensates the fact that you have second-class constraints, so that it is nilpotent. And one can derive this BRST operator from gauge fixed in Green-Schwarz, but the derivation is slightly ugly, and I hope in the future it will be simplified. Okay, so in order to compute anything, of course, we have to know what's the cohomology of this BRST operator. The simplest states are just the massless states. So the massless open superstring vertex operator, of course, is supposed to describe D equals 10 super Yang-Mills. And that's actually very simple to see. If you demanded the vertex operator as Gauss number plus 1, this is the only thing you can write down, which depends on the zero mode. And the cohomology just tells you that A alpha, capital A alpha, can be written in terms of the component fields, which are just the on-shell gluon and on-shell gluino. So dot, dot, dot is just derivatives of the on-shell gluon and gluino. So this, of course, describes the component fields of super Yang-Mills. And if one just takes the left-right product of two of these vertex operators, so that would be lambda, lambda bar, we now have included both the left movers and the right movers, so this is a type 2 superstring. For type 2a, they have opposite chirality. For type 2b, they have the same. Then this A alpha beta is just like the left-right product of A alpha. And it's not difficult to show that states in the cohomology, which now have to be annihilated by both Q and Q bar, describe type 2a or type 2b supergravity states. So this can be understood as a left-right product of this. So if you take two of these, you get the GMN, BMN, and phi field. And then over Schwarz sector, if you go to higher orders, you'll get the Ramon fields and their derivatives. Okay, these are the unintegrated versions of the vertex operators. If you want to compute scattering amplitudes, you also need the integrated version. So in this formalism, there's no BC ghosts, but one can describe the integrated vertex operators using this relation. So U would be the dimension 1 operator, the integrated one, and V would be the dimension 0, one that I just showed on the previous transparency. So for the open superstring, one has this vertex operator. So this is, of course, describes super Yang-Mills. So now I'm using superspace notation where capital M can either be a vector or a spinor index, in which case Ym is either xm with theta alpha. And these are the superspace gauge superfields for super Yang-Mills. So A alpha was the thing I showed you on the previous transparency. And these are actually field strengths. So the lowest component of W alpha is the gluino, and the lowest component of FMN is just the usual field strength for the vector. So this is the D alpha is this constraint that appeared in Green-Schwarz formalism, which starts out as P alpha in the pure spinor formalism. And this is just the Lorentz current for the pure spinor ghosts. If you just look at the first term, this turns out to be the Green-Schwarz vertex operator, but you need these extra terms in order to have BRST invariance. Similarly, the closed superstring vertex operator is just the left-right product of two of these. So it starts out as the G plus B, as in the Green-Schwarz vertex operator, but you need these additional terms for BRST invariance, and this is going to be, the lowest component will be the Ramon field strength, just because the lowest component of this was the gluino. And the order theta, theta bar, you'll see the Riemann tensor, and this is the way the Riemann tensor appears when you compute the 4-point scattering amplitude. Okay, so before going to these applications, let me just say something about some tests. So I showed you at least the massless sector is reproduced correctly. One can go further and compute the cohomology for the massive sector, and by comparing in light cone gauge, one can show that you reproduce the complete GSO plus sector of the superstring spectrum. The next step is, of course, to compute scattering amplitude. So tree level are very straightforward. One loop and two loop need a little bit more work. But in fact, you can show that they agree with the RNS computations. And the two-loop computation is, in fact, much simpler than the RNS computation. So instead of being a 100 or 200-page computation, now it's just a 5 or 10-page computation. And of course, because it's done in superspace, one automatically includes the external fermions, which has not been done yet in RNS. So this equivalence was actually shown by my student Carlos Mafra a few years ago. Now one can ask about, what about in curved backgrounds? So in curved backgrounds, one expects the BRST invariance of the sigma model will imply the low energy equation of motion. And this was verified at least to lowest order, and we expect it to be verified to higher order, and this would give the equations of motion actually in superspace. Finally, one can discuss the background when it's ADS 5 times S5, and this was shown using cohomology arguments that it's consistent to all orders in alpha prime, and in fact has an infinite set of non-local conserved currents to all orders in alpha prime, although the explicit form was not worked out. It was just based on indirect cohomology arguments. Recently, more explicit one-loop computations of these conserved currents were done by Mikhailov and Schaefer Namek. Okay, so now let me get to the first application which I'll describe today, is these higher derivative R to the fourth theorems. So I have to tell you what the prescription is for multi-loop amplitudes. I'm not going to go into too many details, but when there's an integration over the Teichmuller space, so this is like a bosonic string computation. You have the vertex operators here, which here will be for the closed massless states, so the supergravity vertex operators. So I'm computing a 4-point amplitude. I have 4 of these. I have 3G minus 3 B ghosts, and they're so the left-moving and right-moving version. Now these B ghosts in this formalism are not fundamental fields, but they're composite operators, which are defined to satisfy the anti-commutation relation that Q with V is a stress tensor. So that's something similar to what you do in topological string theory from this. Now this N is some regularization, which you need in order to integrate over the lambda alpha and W alpha zero modes. So lambda alpha and W alpha are chiral bosons, and because they're non-compact, if you just integrate naively over the zero modes, you will get divergences. Now, of course, if you integrate over the fermionic zero modes, you will get zero if not all the fermionic zero modes are present. And in fact, one can regularize the divergences coming from the lambda and W integration by canceling them against some of the zeros coming from the thetas and p's. And this regulator does precisely that. I'm not going to go into the details, but you can define it in such a way that it's equal to 1 plus something which is BRST trivial. So since BRST trivial objects don't contribute in this correlation function, one can essentially choose the regulator how one likes, and one can put it wherever one wants on the world sheet, and it should not affect the on-shell amplitudes. This is somewhat similar to picture-changing operators in RNS, where of course one also has to introduce this regulator because you have integrations over the beta-gamma chiral bosons and their zero modes. Okay, so I'm not going to go into the details of this, but the computation of these higher derivative R to the fourth theorems is easily done just by counting zero modes. So for this amplitude to be non-vanishing, the integrand must of course have all the zero modes, including the contribution from the regulator. So the fermionic zero modes we have the 16 theta alpha zero modes. These are scalars on the world sheet. And D alpha are 1, 0 operators on the world sheet. So at each genus you have G of them. So for genus G you have G of them. There are 16 components, so we have 16G. These are the left movers. Of course, you have analogous zero modes for the right movers. So all of these zero modes must either come from the 3G minus 3B ghosts, from the regulator, or from the vertex operators. And now it just comes down to a counting argument. So when the genus is less than or equal to 6, and one does this counting argument, one finds that in order to get something with the appropriate number of zero modes, the vertex operators have to contribute at least this amount of theta alphas and this amount of D alphas. Now it's clear when G is greater than 6, this is not possible. So when G equals 6, it's contributing 16 thetas, which is of course the maximum number. But when G is greater than 6, it turns out this regularization prescription needs to be modified. So one has to regularize not just N, but also B, which is involved with the non-zero modes of lambda. I'm not going to go into the details, but this was worked out in a paper with Nekrasov. So when G is less than or equal to 6, the vertex operators have to contribute this amount. When G is greater than 6, they have to contribute all 16 thetas and 4 D alpha zero modes. Now each vertex operator can contribute at most 1 D alpha zero mode. Of course, one left moving and one right moving if one is using closed vertex operators. So each vertex operator only contributes to this Ramon-Ramon field strength, which has this expansion in theta, as I described earlier. So it starts as a Ramon-Ramon field strength. At order theta, theta bar, you get one Riemann tensor. If you go to higher orders, you start getting derivatives of Riemann tensor. And of course, there are many other fields here. So to contribute this number of thetas, you need to take the derivative with respect to 4 plus 2g thetas and 4 plus 2g theta bars on these vertex operators, on these w's, and just doing the component expansion, it's trivial to see that this comes with 2g derivatives at genus G. So that means that the low energy expansion starts at d2 gr to the fourth. Of course, you can get higher orders in G, because you can get more thetas than you need, but if you get fewer derivatives than this, you won't get contributions because you don't have enough thetas. Now, of course, this only works up to genus 6. For genus greater than 6, the low energy contribution naively starts at d to the 12 for all G. Okay, after dimensional reduction to 4 dimensions, this was shown by Green, Russo, and Van Hove, at least using naive arguments, that this implies that n equals d equals 4 supergravity is finite up to 8 loops. But of course, if this holds, if this is actually non-vanishing, then it won't be finite beyond 8 loops. Now, there may be other arguments that are not based on zero-mode counting, which argue that this is vanishing. But at least from zero-mode counting, there's no obvious reason why this should be vanishing above genus 6. Okay, you can argue this 8-loop finiteness actually without mentioning string theory. You can just look at this superspace expansion. So if we assume that W alpha beta is the gauge invariant superfield of lowest dimension, then this object here is the D term of lowest dimension. I just have to integrate over all the thetas, and you get this number of derivatives. Now, of course, there's no obvious reason why this is the gauge invariant superfield of lowest dimension. You might think that the dilaton superfield is actually the one of lowest dimension, because this has dimension 1, whereas phi has the dilaton superfield has dimension 0. But actually, this assumption is quite natural if you assume that the supersymmetry is related to the supersymmetry in string theory, because if one starts in 10 dimensions and requires the n equals 2 superfields, a left-right product of n equals 1 10-dimensional superfield, then this is actually the lowest thing you can construct, because the dilaton superfield, of course, will be built out of n equals 1 d equals 10 scalars, but there are no n equals 1 d equals 10 scalars in superignos. Of course, to verify this assumption, one needs to know more about off-shell n equals 8 supersymmetry, which is not yet known. Okay, so let me now go to my second application, which is related to these topological A model for A ds5 times S5, and I put the question mark here because this is only understood at the moment for the superparticle. Okay, so let me just start with pure spinor formalism now for the n equals 2 d equals 10 superparticle. So this is the ground state of the type 2b superstring. And these will have 32 bosons because I have my 10 x's, I have 22 lambdas, I have 11 lambdas and 11 lambda bars, so together they give you 32 bosons. And of course I have 32 fermions because I'm doing n equals 2 d equals 10. And I apologize, I have changed notation. So now theta is actually chiral in d equals 10 superspace. It's no longer associated with left movers and right movers for the superstring. Okay, so theta 1 would be left moving and theta 2 would be right moving. So the BRST operator for the superparticle is essentially just the zero mode for the superstring. So it would just be the sum of lambda alpha d alpha and lambda bar alpha d bar alpha. And that, of course, transforms theta alpha into lambda alpha and theta bar alpha to lambda bar alpha. And this looks like something like world line supersymmetry. So it's natural to ask if this formalism actually has some hidden twisted world line supersymmetry where Q plus Q bar would just be one of the supersymmetry generators. Now, in fact, this was actually very closely related to some earlier work of Sorokin, Kajvalkov, and Ziltukin, where they tried to discuss the superparticle with both world line supersymmetry and space-time supersymmetry. Now, in a flat background, this is very difficult to do in a natural way because the B ghost is actually very complicated if you try to write it down. So Q plus Q bar is easy to write down in terms of these variables. But if you try to construct an object which satisfies the anti-commutation with Q is just a Hamiltonian, it's not easy to do. But as I will show for the superparticle in ADS5 times S5, turns out world line supersymmetry in this B ghost can be constructed in a very natural way. And what one has to do is one has to combine these 32 variables, so the 10 x's and the 22 pure spinors, into 32 variables which are now a 16-component complex unconstrained variable. And this will turn out to have some twister-like properties. And now the supersymmetry transformation is just delta theta alpha equals z alpha, where z alpha is unconstrained, and in fact this can be realized as just an ordinary twisted world line supersymmetry. So let me show how one does this for the superparticles. So I apologize, it involves some notation and indices, but it's just a few transparencies. So you want to construct this z alpha and z bar alpha out of x and theta, and the way to do that is to follow the Matsayev-Seitlin procedure and construct this supercoset, but I'm going to choose slightly different parameterization. I'm going to write this supercoset as the product of a purely fermionic coset, which parameterizes PSU224 over the full bosonic subgroup, times just bosonic cosets here. So H and H tilde will just be the bosonic cosets for ADS5 and S5, which don't have any theta dependence. So I'm using the notation that X parameterizes ADS5 and Y parameterizes S5. So C will go from 0 to 4 and C prime will go from 5 to 9. Now we can write these ADS5 and S5 cosets in a convenient way using Pauli matrices as just 4 by 4 bosonic matrices. So A and B will be SU22 indices, which will describe the isometries of ADS5, and J and K will be SU4 indices, which will describe the isometries of S5. So these H and H tildes are 4 by 4 bosonic matrices, and in this notation, the 16 component thetas and theta bars and lambda lambda bars will just decompose into 4 by 4 matrices. So these are like off-diagonal matrices because they transform both under the SU22 and under the SU4. And I've added this gamma 5 here so that this is actually the opposite chirality from theta. Okay, so that's the first step. Now the second step is to describe some kind of twistor transform that mixes the X's and pure spinors into these Z's. So the way to do that is to use these cosets, SU22 over SO41 and SU4 over SO5, to convert the pure spinors, which are naturally thought of as living in the tangent space of SO41 times SO5, into spinors which are naturally thought of as living in SU22 times SU4. And that's done just using these cosets. So the obvious way to do that is just multiply these SO41 times SO5 spinors times this coset. But now you see it has the following property. These lambdas are constrained. They have generically 22 independent degrees of freedom. And the X's and Y's, of course, describe 10 independent degrees of freedom. So Z and Z bar are naturally described in terms of 32 independent variables. But of course, the components of these are just 32 components. So these are generically unconstrained variables. So I've combined my X's and lambdas. This looks something like a twistor transform in terms of these twistor-like 32 component variables, which now transform linearly under the SU22, which are just the conformal transformations. So I can do something similar for the conjugate momentum to Z. So you have to use the inverses to H and H tilde, and they are now going to relate the conjugate momentum to lambdas and lambda bars with these twistor-like variables. Okay, so I'm going to use these Z's and Z bars and these Y's and Y bars in order to now write my superparticle action in a way which I have manifest world line supersymmetry. So how much time do I have? Thank you. Okay, so in terms of this supercoset, which describes equivalently PSU224 over SU22 times SU4, or you can equivalent write it in this way, and these bosonic twistor-like variables, one can show that Q and Q bar, which were the superparticle BRST operators, are mapped to these objects. So this is the natural left invariant current to construct out of this fermionic coset. And it just multiplies Z and Z bar instead of lambda and lambda bar. Now, Q and Q bar naturally have a counterpart, B and B bar, which is just obtained by replacing Z and Z bar with Y and Y bar. And it's straightforward to show that these satisfy the world line supersymmetry anti-commutation relations. So this is very simple. And in fact, world line supersymmetry can be easily made manifest by combining the thetas and theta bars with the Y's and Z's into these chiral and antichiral superfields on the world line. So capital theta and capital theta bar will now depend both on the world line parameter and on Grassmann parameters in the obvious way, and where F and F bar are just auxiliary component fields. So now we have manifest world line supersymmetry, in which Q and B just act as the obvious world line supersymmetry transformations. And now the question is, what does the action look like? Well, that looks nice. If you write the pure spinor, if you start with the n equals 2 superparticle action on ADS5 times S5, using the pure spinor formalism, and you just rewrite it in terms of these superfields, you get this manifestly space-time supersymmetric action. So D4 cap is just the integration over all the Grassmann parameters, and has this nonlinear form. It's not difficult to show that this is actually invariant under all the PSU224 symmetries. And in fact, this world line action can obviously be written as the t goes to infinity limit, where t is the coupling constant, of this topological A model. So it's an A model just because the BRST operator acts with an A twist. So now I'm interpreting theta as worldsheet superfield, and this topological A model can easily be expressed as a gauge linear sigma model. So the gauge linear sigma model involves more superfields. You have to introduce phi and phi bar in this gauge superfield V, but it's introduced in such a way that you can actually use the U4 invariance of this gauge superfield to gauge fix phi and phi bar to be just diagonal, and in that case one just returns to this nonlinear topological A model. So this is a gauge linear sigma model which is constructed based on this purely fermionic coset. And TV is, of course, the usual phi Heliopolis term. Now this was done for the superparticle, and one might ask, well, what about the superstring? So we have, of course, an action for the superstring on ADS5 times S5, but of course that superstring action has a Wess-Amino term, and that gives complications when you try to introduce this n equals 2 world sheaf supersymmetry. So of course this action here has no Wess-Amino term, and it's not at all clear how to relate the superstring action directly with this gauge linear sigma model. Nevertheless, there's an obvious speculation, which is that this topological A model might be useful for trying to study the Maldo-Sena conjecture. So the idea is that there was a gauge linear sigma model which was useful for proving the open-closed duality in the Conofold transition. So this was done by Gopakumar and Vafa and Oguri and Vafa at the end of the last century. And what they did is they used the fact that near t equals 0, t is the modulus which multiplies the phi Heliopolis term. You can get both Higgs and Coulomb phases in the gauge linear sigma model. So this is just a diagram. This is a one-loop closed string amplitude, and you have these disks which describe the Coulomb phase, and the rest is all in the Higgs phase. And what they showed is that the closed string amplitudes can be reinterpreted as just gauge theory Feynman diagrams, where these Coulomb phases are thought of as holes, which can be interpreted as faces of the Feynman diagram. So in their open-closed duality proof, what they used is that the Coulomb phase describes D-branes, and the boundary conditions of these D-branes relate, in their case, 3x's and 3x bars, in a way which identifies these D-branes with just the D-branes you would get from Witten's open topological model for Chern-Simons on S3. So this is a duality which relates to resolved Conofold with Chern-Simons theory. Now there's an obvious generalization to the Maldo-Sena conjecture was actually speculated already in the Gopakumar-Oguri-Vafa papers, which is that there might be a generalization in which now the nonlinear sigma model, or the gauge linear sigma model, is going to describe the superstring on ADS5 times S5. And in this case, the Coulomb phase is going to describe D-branes. So now the linear gauge sigma model is just based out of these thetas. So the analog of this boundary condition is you're going to relate the chiral theta with the anti-chiral theta bar. And that's going to break some of the PSU224 invariance. It will actually break it down to OSP4/4. And it's conjectured that this type of D-brane is going to describe a topological A model, an open topological A model, which is going to describe n equals 4, d equals 4 super Yang-Mills, which has precisely these symmetries on ADS4. So again, the open topological A model is going to be constructed from just a purely fermionic coset, which is going to be the analog of Witten's open topological A model on S3. Okay, so let me just summarize. So what I've argued is that the pure Spinor formalism is useful for computing multi-loop superstring amplitudes and also for studying the superstring in ADS5 times S5. And I presented two recent applications. So when G is greater than 1 and less than or equal to 6, I've argued that the low energy contribution to superstring amplitudes starts at just d to the 2gr to the 4th for the G loop amplitude. And that suggests, at least using naive arguments, that n equals 8 to equals 4 supergravity is finite up to 8 loops, but at least this does not imply that it's finite beyond 8 loops. If I understand correctly, Zvi Bern will just try to give some new arguments why it should be finite beyond 8 loops that are unrelated to supersymmetry. Okay, the second application I discussed is the superparticle on ADS5 times S5 background can be described as actually an n equals 2 world-line supersymmetric sigma model, which can be described as the t goes to infinity limit of this topological A model. And this topological A model is slightly unusual. It's based on a coset which just has fermionic superfields. So of course the fermionic superfields have bosonic superpartners, but at least the lowest components of the superfields are just the thetas. So it's based on this coset, which has 32 or 16 complex fermions. And the idea is to use this topological A model to try to generalize the Gopakumar-Oguri-Vafa proof of the open-closed duality for the Conofold to the Maldo-Sena conjecture. In that case, one has an open topological A model with a different fermionic coset. But there are many crucial points in order to generalize this proof which are still not yet understood. So this is work in progress with Kumar and Vafa. Okay, so I'll stop there.
Thank you very much. Other questions? Yes?
Does finite up to 8 loops mean the problem starts at 8 loops or 9?
9.
Renata?
There is exactly a discrepancy between supergravity construction, which starts with loop number 8. And the reason is that in the construction which we had, it was a Spinor superfield we start with,
Yes.
whereas Nathan has a vector superfield.
Yeah, so I can explain. So
Exactly 4 spinorial derivatives, and this is a jump between loop number 8 to loop number 9.
yes, so I can explain in a few more words. So Renata Kalish had a paper in the early 80s in which she constructed. Okay. So they constructed using a superfield which was not the Ramon field strength as lowest component, but with the dilatino as the lowest component. And that gives a different counting by 1 loop. Of course, in that case, one can't interpret it as a left-right product of n equals 1, d equals 10 superfield. Of course, until one understands off-shell n equals 8, one cannot test which one is correct.
Okay, further questions?
Actually, I just want to make a comment. This is for Renata
Okay.
about her comment. There's a big difference between showing the existence of a potential counterterm due to supersymmetry and the question of whether it exists as a true counterterm of the theory.
Further questions? There don't seem to be any further questions. Then let's thank Nathan again.